All right, so this is the beginning of chapter 2, part A. This will cover atoms, bonds, organic compounds, carbohydrates, lipids, and proteins, and cellular respiration. This unit is a repeat of what should have been covered in the first semester. If it wasn't, it's not my fault. It should have been. It's in the course outline and it is taught when I teach it. So other instructors should be teaching it too. The chemistry chapter should not scare you. It's not meant to be scary. As if you bake and cook, you use chemistry. You're putting things together that are separate and individual, and when you put them together, they come out as something different. Like when you bake a cake, you dump flour and sugar and baking soda or baking powder, etc. Other ingredients depending on what kind of flavor you want, and you put it in an oven and comes out different. So the other perspective that I can offer is that we're going to describe a beach, but we're going to describe it from the perspective of each grain of sand. So don't let it scare you. Don't make it harder than it is, because it doesn't need to be. Okay, so we start with the term atom. Atoms are the basic unit of matter, composed of subatomic particles arranged in specific numbers and locations. The chemists and physicists did not want to redefine the basic unit of matter when they came up with better equipment to look at smaller things. We're going to not look at anything smaller than a subatomic particle because we don't need to for what we're going to look at. The subatomic particles, there's 3 kinds. Elements are specific types of atoms. They're distinguished by the type, or the number of protons. So if you change the number of protons, you change the number, or you change the element that you're dealing with. The known elements are all found on the periodic table of elements. Depending on which textbook, when they were published, there's an international congress that dictates what can be on the periodic table and what can't. They have to exist for a certain amount of time. Most of them have been found in nature. However, some have been created in a lab. You have a periodic table in your textbook. It's in Appendix C. And yes, you're going to need that for at least one of your questions on your chemistry assignment. So you should have your chemistry file, the chapter 2 file, and taking notes on that. You should have printed off the chemistry assignment, and you should have printed off the short periodic table. You're going to need the short periodic table as we go through the notes. You'll have to write and draw elements and molecules and compounds. And so that's why you need to print off that chemistry assignment. Yes, you need to use pencil on that, as if you use ink, I am not going to grade stuff that's been scratched out. You have to erase it, and I want clear, distinct answers. Okay, there are certain pages of your chemistry lecture handout that need to be printed off because you'll be doing some drawings. You're doing some additions, and those should be listed in the directions. Okay, so you have a table in your textbook, and you're going to need this table for part of your chemistry assignment. This lists the most numerous elements in the body. The most numerous, the 6 most numerous are here. You're going to be well versed in the top 4 before this chapter's over, because we focus on those a lot. The rest of these are in the short periodic table, except for iron, which is why you need that full periodic table. I think the largest number of elements I've seen is like 116, sorry. But they can range depending on when they got their information. There's also another part of this table that I didn't include, and that would be the trace elements that are also found in the body. So this column gives it by percentage of body weight, not the atomic mass, not the atomic number, the percentage of body weight. So most of your body is oxygen, carbon, hydrogen, and nitrogen. Oops, there we go. Those are the 4 most numerous components, elements in your body. All right. So 3 kinds of subatomic particles. The first kind is called a proton. The proton has 1 atomic mass unit, has a positive electrical charge, so you can put the P's together. The P in positive goes along with the P in proton, and it's found in the atom's nucleus. Now here, all you need is what is on the slide. There may be other slides where you're going to need more than what's on the slide, because I only put the bare minimum on the slides. So that's why you need to take notes, because there may be other things you need to add. With protons, if you change the number of protons, it changes the element that you're dealing with. Second type of, when we draw the atomic structure, you'll use numbers like a 6 in front of a lowercase p with a plus charge. So a proton can be represented as a lowercase p and a plus charge superscript, a plus superscript. So if you don't know the difference between an uppercase, oops, if I can get there we go, an uppercase and a lowercase, you're going to need to find that out and figure it out, because I expect you to have learned that in elementary school. Your second type of periodic or type of subatomic particle is a neutron. Neutrons also have 1 atomic mass unit. They have no electrical charge. So again, the N in no with the N in neutron. No electrical charge. So neutrons are neutral. They're also found in the atom's nucleus. When we draw a atomic structure, you use a lowercase n with a 0 superscript. So for over here, we would have 6 protons and 6 neutrons in the atom's nucleus. And yes, I'm sorry that this thing decides to give extra lines, but I can't fix that. So you can change the number of neutrons and still have the same element or same type of atom. Just like we gain and lose weight as an individual, neutrons added or subtracted changes the mass of the atom. Okay, electrons are the third type of subatomic particles. They have little to no mass. It takes about 2,000 of them to equal the mass of a proton. They have the negative charge. So if you get electrocuted, it's a negative experience, like watching your niece fly across the floor because she stuck a key in an electrical socket. Now, where the cover, and we still to this day don't know whether it happened or where it disappeared to. Anyway, so she got an electrical burn. Then I had to deal with the stupid pediatrician because he wanted to know if she was acting funny. And I was like, yes, she's acting different. She's sitting there being quiet. This is the child is not a quiet child. It's not the one that usually sits down and doesn't do anything. She was the wild child running around screaming like a banshee sometimes. Anyway, and yes, I've been telling that story for almost 30 years, 29 years, because she'll be 30 on her next birthday. Anyway, so they are found moving in orbits around the atom's nucleus. We also call them shells. So over here, these two blue things would be moving around and around and around. These would all be moving around and around and around. Because they're moving, we also call that energy levels. We also refer to them as shells. Now, okay, plugged it back in. All right, so with the orbits, the faster they go with more energy, they take up more space. When they go slower, they take up less space. So we talk about orbits, we talk about energy levels, and we talk about shells because they're in layers. Now, just like with neutrons, you can change the number of neutrons and still have the same element. However, keep in mind that when they gain electrons, they're going to become more negative. When they lose electrons, they're going to become more positive because they take that electrical charge with them. So if you lose negative electrons, it makes you more positive. If you gain electrons, if you gain one electron, it means you have a negative charge. If you gain two, you would have a 2 negative charge. So if you lose 3 electrons, you're going to have a 3+ charge. Okay. Isotopes are atoms that have lost or gained neutrons. So they have a different mass. Here we have hydrogen as it's typically found with 1 proton and 1 electron. Here we have heavy hydrogen where you've got a proton, a neutron, and an electron. So it's got a different mass. So this, is what we see here, and this is the other one. The 2 and the 1 deal with the atomic mass. So typically carbon has an atomic mass of 12. Carbon 14 is used to figure out how old something is. It's got 2 more neutrons than typical carbon. The way we encounter most isotopes is in the form of the radiation that they emit. So if someone has an X-ray, they're exposed to an isotope. If someone has radiation therapy, they're exposed to an isotope. It doesn't change other chemical behavior. It just adds this extra property. So isotopes found in nature, Some have been created in labs, but they do exist. So you have atomic number versus atomic mass. Atomic number is the total number of protons in the atom's nucleus. That tells you what element you're dealing with. Atomic mass is the average number of protons and neutrons found in the atom's nucleus. So with atomic number, it's just the number of protons. Sorry, the fireworks are still going off here. Atomic mass is an average proton plus neutron. So isotopes exist in nature. They take that into account. They take into the account the percentage of isotopes versus a typical atomic mass in nature. So you'll see decimal numbers. With decimal numbers, 0 to 0.5, you leave the number alone. If it's more than 0.5, then you can add a number, add 1 to the whole number. But you can't have part of a neutron. So rounding more than 5, so 0.51 up to the whole number, you can add and go up. So it has to be more than 0.5. Okay, on that small periodic table, you have 4 rows. In the bottom row, you have 2 boxes that are filled in, and then you have this big empty box here. In that box, you need to put this equation. Atomic mass minus atomic number tells you the number of neutrons. So instead of P, or protons rather, you can put the lowercase p. Instead of neutrons, you can put the N with the 0, P plus, and 0. Either way, that equation needs to go down into your, put onto your periodic table so that you have that available as a reference. All right, so the periodic table. Each box contains the name of the element, the chemical symbol, the atomic number, and the atomic mass. For chemical symbol, you'll need uppercase or uppercase and lowercase. You need to make sure that you don't just draw or make a short, because that would be wrong. Make sure you can tell the difference between your uppercase and lowercase. Uppercase S, lowercase I, uppercase S, uppercase I. Those are not the same thing. This one is silicon, an element. This is a molecule of sulfur and iodine. Not the same thing. Chlorine has capital C, lowercase l. To make sure we can tell the difference between your uppercase and lowercase. Okay, atomic number. In the box, you need to find helium. Should be upper right corner. At the top of the box, you have a 2. That is the atomic number, and you need to label this on your periodic table. Atomic number, which is the number of protons. And then you have the chemical symbol, and at the bottom you have the number 4. You need to label that as the atomic mass, which is protons plus neutrons. So again, that's why you should have printed it off so you can add that. The rows which go across are going to tell you the number of electron shells or orbits found in the atom. They get distinguished with Arabic numbers 1, 2, 3, 4. The columns, on the other hand, go from top to bottom. They're going to get distinguished with Roman numerals. Capital I is 1, 2 capital I's is 2, all the way up to V for 5 and 3 ones for 8. All right. So that tells you how many electrons are in the outer shell or valence shell. Okay, so if you take a look at your little periodic table, you need to add the distinction for column, both the numbers and what column tells you, and you need to add the distinction for rows and what that tells you. So rows is the number of electron shells, and columns is the number of valence electrons. Now, the closest shell to the nucleus is always considered or labeled as number 1. There are 2 boxes in the periodic table or in the first row. So that means there's going to be up to 2 electrons in that shell. There are 8 boxes full. That tells you there's going to be 8 electrons in that second shell, unless it only has 2 shells, and then the outer shell is going to be whatever column it's in. If it has 3 shells, it'll have 2 electrons in the first shell, 8 electrons in the second, and then whatever column it's in, that will be in the third. If it has 4 shells, like down here, oops, then it will have 2 electrons in the first shell, 8 in the second, and oops, 8 in the third, and then whatever column it's in. So the number of boxes filled in with elements tells you how many electrons are in that shell. If it's full or stable is the term that we use. So we use the periodic table to draw the atomic structure. You need to draw, have the space divided into 3 pieces, because I'm going to do one as an example and then give you the opportunity to practice drawing 2 more. Okay, so if we draw boron, it has an atomic mass of 5. And no, you don't have to memorize the periodic table, but I've been doing chemistry for the last 40 years. So yeah. So that's going to be its atomic number. If we look at the atomic mass, it has an atomic mass of 11. It's in the row 2. And it's in column 3. Oh, poop. Again, I can't help the extra lines it adds, but there we go. So that means To come up with an atomic structure, we have 5 protons. We have 11 minus 5 . So we have 6 neutrons in the atom's nucleus. There are 2 rows or shells. I know you don't have to be perfect at drawing. The first shell is going to have 2 electrons. You can either use an E with a negative or you can use a ball. I don't care which. One of them should make sense. Then for the valence shell, you're going to have 3 electrons, and I always put them in pairs because it's easier to count. You can also draw this in a single color. So 5 protons, 6 neutrons in the atom's nucleus, 2 shells, 2 electrons in the first shell, and you can do that with the deeper ones, but with the valence shell, you're going to have to make sure that the electrons are independent of each other. I will count it wrong if you put 3E or 3 dots. Okay, so let's also have you draw sulfur and potassium. And so yes, it's going to go quiet because I expect you to try and draw them on your own. Okay, so with sulfur, you have 16 protons. You have 32 minus 16, so 16 neutrons in the atom's nucleus. You're going to have 3 shells. You'll have 2 electrons in the first shell, 8 electrons in the second shell, and you'll have 6 electrons in the third shell because that's the column it's in. Okay, so then potassium. and potassium's going to be kind of big. So 19 protons, 20 neutrons in the atom's nucleus. 4 shells. So 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, and 1 electron in the valence shell, because potassium's in the first column and the fourth row. So that's how you draw the atomic structure of an atom. You can also use atomic structure when you draw molecules. Now, atomic stability. An atom is stable when it has 8 electrons in the valence shell, except for the first shell. There's an equation you can learn. If you take a full chemistry class, then you'll get into that. But for our purposes, the first shell can only hold up to 2, and the rest of them 8, up to 8. The atoms can gain, lose, or share electrons to become stable. So this is in the first column. It has 1 electron. The easiest way for it to become stable is to lose that electron. However, that means it's going to gain an positive charge because it will have 8. It'll have 11 protons. It starts out with 11 electrons. But if it loses an electron, that means it's going to have 10 electrons. So then it has a net positive charge. Okay. Everything in column 1, that's one way it can become stable, is to lose that electron. Everything in column 2 can lose 2. Everything in column 7 needs to gain 1 or share. Everything in column 6 needs to gain 2 or share. If it gains 2, then it's going to have a negative 2 charge. Because 8 is the magic number, we call it the octet rule. Octet rule states that an atom is going to react in order to become stable, which is to have that 8 number, that 8 electrons, except for the first shell, which is only 2. Now, OCT, the root, OCT, here we go. Is associated with the number 8. Some prefixes are associated with numbers. On the second part of the information with that small periodic table is some roots. Some of them are associated with just the number of carbons, and some are associated with the number. So you have meth, which means methyl or meth, which is associated with 1 carbon. Eth for 2. You have prop and I don't remember all of them now, but you've got hex for 6, pent for 5. Those are associated with just numbers, but the meth and the eth and the prop, those first 4 are all going to be associated with numbers of carbon. Okay. Next, we have chemical formulae. Chemical formulae is plural, formula is singular. There are 2 representations that we use with formulas. So a molecular formula is a representation of a molecule where you use the chemical symbols and subscripts to indicate the number. So in the subscripts, it's after the chemical symbol. So H2O means you have 2 hydrogens and 1 oxygen. CO2 means you have 1 carbon atom and 2 oxygen atoms. So the subscript goes with the atom listed previously to that. So C2 means 2 carbons, H6, 6 hydrogens, and 1 oxygen. Tells you what's in the molecule. Structural formula is a way to represent a molecule using the chemical symbols and lines to indicate the bonds and the shape, possible shape of the molecule. So here you have 2 different structural formulae, but you only have 1 molecular formula. And this illustrates the difference between ethanol, which has OL at the end, which means it has an OH group, which is the alcohol group. And you have ethyl ether. Ether means that you have a carbon and 2 oxygen, an oxygen, between 2 carbons. So the carbon is bonded on one side of the oxygen, the other carbon's bonded on the other. There is a certain number of lines that each of them can have, and that indicates the number of bonds. Now, I don't care what your structural formulas look like, formulae look like. I just want them to have the correct number of atoms and the correct number of bonds. The OH group that we see here could have been placed over here or somewhere else on the molecule for what we're doing. If you were in a chemistry class, it's going to matter, because if you try and put ethanol in a flame and burn it, you'll see it burn. If you try and do ethanol, it's going to explode. So you can put ethanol in your gas tank, your car will tootle along down the road. If you try and put ethyl ether in your gas tank, it's going to explode the car when you turn it on. So different structural formula means a different chemical, different properties. However, like I said, when I ask you to draw it, I'm not asking you to do any chemical experiments with it. So I don't care what it looks like, as long as you got the right number of bonds and the right number of atoms. Okay, so our 4 most numerous elements in the body, you're going to have to do the atomic structure and potential structural formula for each of the 4 most numerous elements in the body. So you've got 4 spaces. The first one needs to have hydrogen. Hydrogen has 1 proton in its nucleus and it has one electron in its valence shell. In a structural formula, oops, there we go. You're going to see a capital H and a line. It doesn't matter which direction the line is, but it's only going to have one line. In one of the bigger boxes or areas, you need to draw oxygen. Oxygen has 8 protons, 8 neutrons in its nucleus. It has 2 electrons in the first shell and 8 electrons in the second shell. So it's got an opening, for 2 more electrons. So it needs 2 electrons, or it needs to be in 2 bonds. So it needs to gain 2 electrons to become stable, or it needs to share. In a structural formula, oxygen will have 2 lines. You can have 2 single bonds, or oxygen can have a double bond. So sharing 2 electrons, pairs of electrons between those. But somewhere around oxygen, it should only have 2 lines. In the other big box, you're going to need to draw nitrogen. Nitrogen has 7 protons, 7 neutrons in its nucleus. It has 2 shells. The first shell has 2 electrons, and the second shell has 5. So 8 minus 5 means 3 is the magic number for nitrogen. In a structural formula, nitrogen can have, 3, oh please. Nitrogen can have 3 single bonds, or it could have a double bond and a single, or it could have a triple bond with something else. So then you have, in another small box, you can put carbon. Carbon has 6 protons, 6 neutrons, 2 electrons in the first shell, 4 electrons in the second shell. So 8 minus 4, it needs 4 bonds. So carbon, where are we at? Carbon can either be in 4 single bonds, or carbon can be in a double bond and 2 single bonds, or, and again, it doesn't matter which direction, or carbon will be in 2 double bonds. You don't typically see carbon in triple or quadruple bonds. So those are your 4 most numerous elements in the body. Now, the shortcut for remembering these 4 most numerous elements in the body is if you can remember HONC, HONC, 1, 2, 3, 4. Hydrogen needs 1 bond, oxygen needs 2, nitrogen needs 3, carbon needs 4. So if you're asked to draw the structural formula, you start with carbon because it needs the most bonds. You put hydrogen on last. You can't add elements. You just work with what they've given you. And so you have to manipulate and move things around. So again, you may need double bonds somewhere. You may need just triple bonds, but HONC is the shortcut to remember bonding potential for the four most numerous elements in the body. Okay, one way we can form molecules is with ionic bonds. Ionic bonds are attractions between atoms that have transferred one or more valence electrons. This generates oppositely charged ions. So ionic is an adjective. A cation is an atom that has lost one or more electrons, and it's going to have a positive charge. You have to draw that on the atomic structure and the structural formula. So it's going to have a positive charge. Cation is a word that has a T. A T looks like a positive charge. It's typically named first in a compound. An anion is an atom that has gained one or more electrons, so it's going to have a net negative charge. Anion is a word with two N's for two negative. Anion looks like onion, and if you have onion breath at the wrong time, that can be a negative experience. And yes, that's how you remember things, making them funny, making them tie into something else that you know. So here we have a place, and you've got a place in your outline. However, instead of atomic structure, we're going to draw Lewis dot structures. So we're going to do a couple of these because you should have enough space. So sodium chloride, which is what we just saw. Sodium okay, sodium Na is going to have a single dot because it's in the first column. Chloride is Cl, and it's going to have 7 dots. Okay, so that's the two separate ones. When we draw them together as a compound, oh well, chlorine is going to have seven of its own electrons, and okay, where am I at here? There we go. And it's going to have one, oops, one of sodiums. So it's going to wind up with a negative charge. Sodium, on the other hand, is not going to have any, and it's going to have a plus charge. See if I can do this real quick down here. Sodium, it's going to have a plus charge. Chlorine is going to have a negative with 8 electrons around it for sodium chloride. All right, another example would be, let's see, beryllium with 2 of them, oxide. So oxygen is going to have 6 of its own electrons. And then we're going to have a beryllium who is, no, that's not right. It's only going to be 1 beryllium and 1 oxygen. So beryllium has 2, but it's going to give those 2 to oxygen. So oxygen winds up with a -2 and beryllium winds up with a +2. Okay, so if we look at lithium oxide, that's going to have 2 lithium and 1 oxygen. The oxygen is going to be in the middle. It's got its 6 electrons. There are going to be 2 lithium. Lithium has 1 electron in its valence shell, and it's going to give it, so it winds up with a plus charge, and oxygen winds up with a negative, and the other lithium is going to give up its electron, so it's going to have a plus charge, and oxygen winds up with a 2 negative charge. Okay. Potassium and fluorine. So potassium, nope, that's wrong. Two potassium, one fluorine. Dang, I'm messing this up. Let's see. Okay, so potassium, not potassium, calcium. Here we go. Okay, so calcium, where am I at? Oops. Calcium chloride. It's going to have 2 chlorines. So calcium starts off with, calcium has 2 electrons in its valence shell, and each chlorine is going to have 7. So we put calcium in the middle, and the 2 chlorides are going to be on the outside. Okay, so this is going to produce the chloride, which is going to have 7 of its own on either side. And then we put the calcium in the middle. It loses 1 electron to this chlorine, making it negative, and calcium positive. It loses a 2nd electron to this chlorine, making it negative, and so it's going to have a 2 plus or a plus 2 for calcium chloride. Okay, now ionic compounds can dissolve into water or other solutes or solvents. They become the solute. So, because they can dissolve into into solvents, especially water, that means that their electrical current can be carried in that water. So, another term that we use to refer to electrolyte or ions is the word electrolyte, referring to that electrical charge that they can conduct in water. In chemistry, electrolytes are compounds. In medicine, we look at the individual ions. In the name of the electrolyte, the cation is always named first. The anion is named second. So this is another table that you're going to need for part of your chemistry assignment, because you're supposed to write down the ionic composition of the electrolytes. So calcium ions are Ca with a 2 plus. Chlorine ions are Cl with a negative. And that's in lowercase l, not an uppercase I. Sodium. Now, sometimes you have a molecule that has a net charge. This is phosphate, HPO4 with a negative 2 charge. So yes, we have to be able to distinguish between your subscripts and your superscripts. Another molecule that has a charge is bicarbonate, HCO3 with a negative charge. Not all of the electrolytes are on this table, but most of them are. Some of them you'll have to use some of your notes, at least for 3 of them. The hydrogen, hydroxide, and carboxyl ions are not in this table. All right, so that's the end of part A of chemistry.